Hey guys, my name's Dr. Paul Rimmer. Welcome to the High Rate Athlete channel, and today we are going to discuss how do we know how much fuel we're using during exercise, how do we know what fuel dominance we have during exercise, and how can we maybe use this to our advantage. So we're going to get into a little bit of biochemistry first. So if we get a bit worried about biochemistry, I'm going to keep this as simple as is possible. So during endurance exercise, in particular, across many forms of exercise, our two main fuel sources are going to be carbohydrate or glucose in the form of blood glucose or glycogen stored in the liver or muscle, or it's going to be fatty acids. And this is going to be dependent on the intensity of exercise at which we are taking part. Okay, I'm not going to get into that today. I just want to talk to you about what I do here in my lab. Nexus Performance Clinic here in Leeds. I'm going to talk about what I do in my lab and how we use this data to work on fueling strategies, but also training strategies as well, and nutrition strategies in order to maximize athletes' performance. So let's get onto the topic. Let's talk about this idea of fuel usage. To start this whole conversation, we're going to talk about something called the respiratory exchange ratio, RER. Okay? So RER, alright, it's nice and big, excuse my handwriting, is equal to our amount of CO2 that we produce divided by our oxygen consumption. Okay? So, first and foremost, when we're testing this in the lab, what we do is we put on an oxygen mask, not an oxygen mask, sorry, a respiration oxygen collecting mask or a gas analysis mask, sorry, excuse me, a little bit hay fever this morning, it's got me the sniffles. And this measures on a breath by breath basis how much oxygen that we are taking in and how much carbon dioxide we are expelling or expiring in our breath. And this is an important ratio. We're going to show you today how to work out this number and then what we can do with it moving forwards. So now we know we breathe in oxygen and we breathe out CO2, and a number can be calculated, or respiratory exchange ratio can be calculated by dividing our CO2 expired by our oxygen uptake. Well, how does this relate to specific fuel usage? How does this relate to the ratio of carbohydrates to fats, for example? Or, more importantly, what proportion are we using? And then how do we extrapolate that out to actually work out how much energy, one, we're producing, and two, how are we going to replace that energy? And three, at what intensities, what mix of fuels, carbohydrate and fat proportions, are we using at different intensities? So maybe that would guide, how we would work our training interventions off that. I'm not going to go that much deep depth in today. I'm just going to talk about the very fundamental principle of this respiratory exchange ratio. I just wanted to give you an example of how we might use that moving forwards. Okay, so let's talk about carbohydrates first. So, in this case, we're going to talk about glucose, and the molecular formula or chemical formula for glucose is C6H12O6. Okay, so that's a molecule of glucose. Now, if we were going to fully oxidize that to produce as much energy, or ATP, so ATP is the body's energy currency, to fully oxidize that, we need 6 molecules of oxygen, so 6 molecules of O2. And that gives us 6 molecules of CO2 plus 6 molecules of water plus 38, I'm not backing myself now, 38 molecules of ATP. So that's our energy currency there, okay? So now we've got that, what we should be able to see, if we're very clever or can just see, is if we look here now, we've got 6 molecules of CO2 and we have 6 molecules of oxygen here. So if we take this number and divide it by this number, what we get is 6 divided by 6, which equals 1. So our respiratory exchange ratio for glucose, if we're completely oxidizing glucose, glycogen during exercise, is 1. So if on a breath by breath analysis, if we're testing an athlete, and this number that we're seeing here comes out as 1, that means that we are pretty much just relying entirely on our glycogen metabolism or carbohydrate metabolism, okay, to produce energy for exercise, to produce this rate of ATP. Now, let's talk about fatty acids, okay? So fatty acids, there's a few bigger numbers involved. So for most, fatty acids will differ because there's different chain lengths and things as well. So I'm just going to talk about the most commonly used length of fatty acid chain, and that is, we have C18, H32, you're seeing a commonality, the hydrocarbons, H32, and then it's O16, 16 maybe? O16, my brain's not working now. It's not O16, that's how many molecules are produced. Bear with me guys, O2. Okay, so from this we get, so similar points again, sorry, so to this we add an amount of oxygen. Okay, so we're trying to fully oxidize this fat. To do that we require 23 molecules of O2. Okay, do you see the difference there? Hopefully you can start to see now that we require a lot more oxygen, which takes a lot more oxygen delivery to fully oxidize fatty acids, okay? And that gives us 16 CO2 plus 16 H2O, is that right? Plus 138 ATP. So what do you notice here? Firstly, fatty acids give us much more energy than carbohydrates do per molecule, if you will. But what you also notice is that it requires a hell of a lot more oxygen in order to produce that energy. So if we have a high oxygen demand, if we want energy to produce quickly, that's why we switch from mostly fatty acid oxidation at rest, and we've got plenty of breath, plenty of oxygen availability, plenty of time to relax, plenty of time for those cells to saturate themselves with oxygen to fully oxidize fatty molecules. But as our energy demand increases, okay, energy demand goes up, and we require oxygen to be utilized fully, because again, we're not fully utilizing all the oxygen, and I'll show you that in a second. That then all of a sudden we need to switch to something where we are fully oxidizing our energy sources, and although there's a lower amount of ATP that's produced, the rate at which the ATP produced is much higher, much faster, much quicker, okay? So let's flip it back now and let's think about this respiratory exchange ratio. So we're going to do exactly the same of what we've done here. So here we have our 23 O2, and here we have our 16 CO2. So if we then go 16, I'll write this the other way around, it's a bit easier. So if we go 16 divided by, so this number here, divided by this number here, 23 is around about 0.7. Okay, so that means if we're oxidizing fatty acids fully, really chilled out, really low intensity exercise, almost at rest, our RER for this is 0.7. RER, put that there for clarity, equals 1. So now what do we do with this? Okay, now there's some other maths that we need to talk about here as well. I'm not going to go too much into those, but what I am going to tell you though is what we do know is we have what are called R values or RER values. So with our RER at 1, so we're going to change pen colour slightly, going to go red now. So with an RER of 1, that means that we are producing, that is the equivalent of 5 calories, 5 food calories, kilocalories, or big C calories, depending on what you call it, per litre of O2. So that means if we know our RER value, and we know how much oxygen we're consuming, which we do from our breath by breath analysis that we did at the start, using our oxygen mask and our metabolic analysis kit, that means that if we know our RER is 1, we're burning 5 calories for every litre of oxygen that we take up, we can work out how many litres of oxygen we're consuming because we have that number, and then all of a sudden, bish bash bosh, we know how many calories we're burning per minute, per hour, per whatever at a specific intensity. Now, we then have a chart or a table which then will give us our calories per litre of O2 at different RER values. So I'm not going to go through all of them now, but if we look at the fatty acids as an example, the 0.7, so an RER of 0.7, just before we finish this, well, what do we think that would be? If we know the higher intensity switches towards more carbohydrate usage, there's lower energy being produced for each unit, but we also know that the rate of energy is increased, right? There's more energy demand, then that would mean, do we think that a lower RER, so there's lower energy demand, okay? Because we're not reliant on switching to carbohydrate metabolism, do we think that this RER value at 0.7 is going to be more or less calories per litre? So have a think about that. Pause the video if you want. And the answer is that it's lower, okay? It's lower for the reasons we've just discussed, okay? Because you're at lower intensity, energy demand is lower, so you would expect, if our maths is right, a lower RER, and this comes out at around about 4.7, I think it's 4.69, if my memory serves me correctly, calories per litre of O2. Now, they've done lots of tables, lots of charts, and there'll be a full chart ranging every value of RER from 0.7 all the way up to 1. And from that, at any specific intensity, we can then work out how many calories per hour we're using, but not just that, we can also work out the dominance of the fuels that we're using as well. So how might we use this? Well, it's pretty obvious, right? If we know our RER values and we know our intensity, we can then reverse engineer that to know how many grams of, say, carbohydrate we're using per hour at a given intensity, or how many grams of carbohydrates and fat we're using at a given intensity. And that might then mean, okay, if we know how many grams of carbs we're using, can we put all of those carbohydrates back in through feeding strategies to help prevent, or help delay, prevent's not the right word, maybe help delay fatigue in like longer endurance events. It might also mean that if we've got an athlete who is a carb burner at quite low intensities, is there anything that might point towards in terms of our training or in terms of our nutritional strategies to maybe get them more fat adapted, okay? So things like train low and things like that. Or is it that we've got an athlete who we want to be highly glycolytic, a sprinter, 400 metre, 800 metre runner, we've got a sprinter and they're not switching to glycolytic metabolism, that RER is staying low even at high intensities, which means they're not switching on this system as much. So the assumption that a lot of people make is that we always want to be oxidizing more fat more of the time. And that's certainly true in most endurance events, okay? Because that's going to be glycogen sparing, which then allows us to go and perform or do those bursts of higher intensity effort, like, you know, for example, cycling going up a big hill. Problem is, in certain sports, we don't really care about fatty acid oxidation. We don't. We need this glycolytic system switching on. We want it switching on fast, we want it switching on early, we want it switching on hard and aggressively, okay? So you'll see a lot of research about how to improve the threshold at which we switch. That might not be appropriate for all athletes. So when we're doing our programming, we're doing our testing, we have to be very aware of what we're doing and why, and that just because we get an improvement doesn't necessarily mean that's going to benefit performance, in the sense that we need to understand the athlete's demands, what the training objectives are, and ultimately what their performance objectives are. Right guys, hope you enjoyed that episode of Sports Science Shorts. Hopefully that all made sense. And what I'm going to come back to in the next episode is I'm going to show you guys, instead of having to use metabolic analysis, I'm going to show you a way of estimating all of this stuff so you too can work out approximately how many calories you're burning per hour and roughly what kind of fuel usage that would be, looking at more general data. So if you don't want to do metabolic analysis, this is the next best thing to look at. Anyway, if that was useful, please give this video a like and a subscribe, and I look forward to speaking to you wonderful humans again at some point very, very soon. Peace.